All right, let's wrap up this chapter, chapter 6. Final part is we're going to talk about two types of collisions, elastic and inelastic. So far, we've only really been considering inelastic collisions, uh, and now we're going to include some elastic collisions. In elastic collisions, energy and momentum are conserved. And so the objects bounce off of one another, and no energy is lost to sound, no energy is lost to heat, no energy is lost to the deformation of the objects. You know, there aren't really very many examples of this in the whole universe, really, or at least in the world that we live in, but there are some, and one of those is the collision between gas particles. And the main reason that they're uh, elastic collisions, that means that they have conservative forces that are being used, right? Remember, conservative forces conserve energy, and elastic collisions, the forces involved conserve energy, and so they have conservative forces. And if you recall, there were these two broad categories of conservative and non-conservative forces. Well, conservative forces conserved energy, and they were largely field forces. So when gas particles collide, they're not actually colliding, but instead, you know, they're coming close to one another, and then they sort of miss one another because of the interaction of their electric forces, because they're charged particles, and they then they never actually touch one another. So these collision of gas particles are an elastic collision. We often approximate collisions as elastic. For example, the collision of billiard balls. You know, apart from the sound that you get when billiard balls collide, and it doesn't take much energy to make a sound, but apart from that, there's really no other energy loss. The billiard balls don't really heat up, they don't deform in any measurable way, and so that's pretty much a conservative or an elastic collision. So elastic collisions conserve both energy and momentum. And some examples are like the collision of gas particles. And then we can approximate some collisions, such as the collision of billiard balls or other hard objects. Now, inelastic collisions, which includes all other collisions, only momentum is conserved. Right? So energy then is not conserved. And these include every other collision in the universe. Every collision of every particle in the universe is inelastic, at least. And then there are some, those that involve conservative forces, that conserve energy as well. And so those are elastic collisions. Inelastic are, you know, for example, the collision of two cars. When I have these two cars that collide with one another, even though they get really messed up in the front end and lots of energy is lost, and so they don't conserve energy, they still do conserve momentum. The total momentum of the system, despite all the energy that's lost, the total momentum of the system is conserved. All right, so inelastic collisions, only momentum is conserved, energy is not conserved. Let's look at a particular type of inelastic collision, and that is a perfectly inelastic. Let's see, do I have something else in here? No. Perfectly inelastic collision. And a perfectly inelastic collision is just one where the objects stick together. All right, remember, inelastic, only momentum is conserved. And when it's perfectly inelastic, that just means that the objects stick together. It's a particular type of collision. It's really worked out in the same way as we've been doing with the conservation of momentum, but it's actually made a little bit easier. So consider this, that I have two objects, M1 and M2. They have velocities. They're going in opposite directions, one to the right and one to the left. And then after the collision, they stick together, right? And then my net momentum after they stick together is going to equal to m1 is going to equal m1 times v1 plus m2 times v2. But since they stuck together, they have the same velocity. So I can just say that this is m1 plus m2 times the velocity. Okay. So the objects stick together upon colliding, so they both have the same velocity. And it works out in much the same way. I think I have an example here in just a moment. Actually, no, I don't think I do have an example. Let me look. Let's work one out. We'll just put in some numbers so you can have some practice with this. Let's say that I have a mass here of 1 kilogram, and I have a velocity of 10 meters per second. And here I have a mass of 2 kilograms, and I have a velocity of 3 meters per second. Obviously, this is going to the left, so it's going to be negative. Now, I want to know what is the velocity of them afterwards. Now, I can calculate what is the net momentum. That's going to be m1 v1I plus m2 v2I. That's going to be 1 kilogram times 10 meters per second plus 2 kilograms times negative 3 meters per second. It's 10 minus 6, which is 4 kilogram meters per second. All right, so that's my initial momentum. And then in the final state, it's going to look like this. My initial momentum will equal my final momentum. I've already calculated my initial momentum. It's 4 kilogram meters per second. That's going to equal the total of the mass, which is 1 plus 2, times the velocity. All right, so the velocity then is going to be 4/3 meters per second, and it's going to be to the right as positive. These work out just like the previous problems that we've done in conservation of momentum, the only difference being that the two particles have the same velocity, and so they're actually a little simpler. Let's fill this in. Momentum is conserved. Momentum is conserved in every collision that has ever occurred or that ever will occur, but energy is not conserved. All right, you have a homework problem where you have to use this fact. You have to say that PI, or excuse me, apart from this, in elastic collisions, you have a homework problem. You'll see it, where you have to use the fact that PI is equal to PF, and then you also have to use the fact that the initial energy equals the final energy. And all of classical thermodynamics is built on that assumption. And so you can characterize the motion of gases, gas particles, in an ideal gas, and characterize their thermal energy by looking at those two facts. All right, let's see here. Oh yeah, try this at home when you're able. Take a ball and you drop it. You drop a small ball and then you drop a big ball, and they both bounce about to the same. Then take a ball, your big ball like a basketball, and then like a little tennis ball, and drop it. You don't need to drop it far, a meter or so, and see what happens. Right? This is what's going to happen. Your big ball is going to bounce up just a little bit, that basketball, but this guy is going to shoot way up in the air. Right? This is really kind of cool. Kids really like this. If you do it just right, it takes a little bit of practice, but if you do it just right, that ball will shoot way up into the sky. Okay. And then, like, if you want to amaze them even more, then you explain it in terms of momentum. You see, you have a momentum vector here that's traveling downward. This has a big mass, and this has a little bitty mass. But they both have the same velocity. But because this one has such a bigger mass, its momentum vector, when it comes back up, when it comes up, is big. And it transfers all of its momentum to this little bitty ball. And since that little ball has a smaller mass, it shoots off at a very high velocity. All right, so it has a small mass, and so it gets a very big speed going up. So it's just simply a transfer of momentum from the large ball, which has a large mass, not a very high speed, but a large mass. And so it makes that momentum of that big ball bigger, and it transfers that large amount of momentum to the small ball. And since the small ball has such a small mass, it gets a very high velocity. Try it out. It's kind of cool. And I think that's the end of this chapter. You should be working through the homework, working through the old test questions, and that's all.